Hello everyone, thank you for tuning in today. My name is Daniel Lee and I'm a PhD student from the University of Florida, and today I will be talking about single agent indirect herding of multiple targets using metric temporal logic switching. And before I move on, I'd like to give recognition to my co-authors, Zhu Xing, Dr. Bridgman, Dr. Zavlanos, and my advisor, Dr. Warren Dixon. Zhu Xing, Dr. Bridgman, and Dr. Zavlanos are from the Duke University, and Dr. Dixon is from the University of Florida. In today's presentation, I'll be talking about control of switch systems. Switch systems can be represented as a family of differential equations where the dynamics are parameterized by this index P, and P denotes some operating mode the system is in. And often we can control what operating mode the system is in through the switching signal sigma. And in typical switch system analysis, we can develop stability conditions that place constraints on the switch signal. And if we satisfy these constraints, we can ensure stability of our switch system. And a couple of these conditions are shown right here. This first one is a dwell time condition. And what a dwell time condition says that if we look at consecutive switching instance, if we bound the amount of time that a system is in a particular mode, then we can ensure stability. And if we want to look at an average dwell time, for example, where instead we look at an interval of time, and what that says is we bound the number of switches in that interval of time. However, the problem is that these conditions are only sufficient conditions and they lack a constructive method to actually design a switching signal. So the goal in our work is to design a switching signal that admits a certain behavior or specification, meaning that it gives us a way to determine how to switch between modes. Here's an application in a multi-agent system where there are multiple target agents, which you see in yellow and pink, that are scattered in the room. The goal, as you see, is for the quadcopter to force the target agents to the center of the room. And since there's a discrete change in the target agent's motion based on when it is being chased or not by the quadcopter, we pose this as a switch system model. And to solve this problem, we use a combination of switch system Lyapunov-based design with formal methods. And specifically what we do is we use Lyapunov-based control design to develop a control law for the quadcopter, provided we tell the quadcopter which target to chase down. So then the question is how to design a sequence of actions that tell the quadcopter which and when to chase each target. And the solution that we propose is to pose the dwell time conditions as temporal logic based specifications. Then we use formal methods tools to generate a sequence of actions that satisfy our stability criteria for the quadcopter to execute. So now I'll go into some of the basic semantics and notions that we want to characterize with temporal logic, with the goal in mind that we are going to use this language to encode a high-level specification. And there are various kinds of temporal logics out there, and a fairly common one that we will first look at is linear temporal logic. So in LTL, we want to look at sequences of events. What we want to do is write down formulas about the events that occur. So we'll define a couple of operators. The diamond operator here on the left means eventually. And what that means is some proposition is true if at some point in the future that property will become true. And the box operator means always, meaning for all sequences of events the property must be true. So here on the right you see A is some proposition, and if I want eventually A, looking at a possible sequence, we may have not A, not A, not A. Then when A is true, any sequence after that is arbitrary as we've satisfied the proposition. Then for the formula always A, to satisfy this proposition, A is true for every event in the sequence. And as I was saying, LTL is sequence-based, so there is no notion of time and when these events happen. So another temporal logic which we adopt in our framework is metric temporal logic. And the notions we discussed on LTL is very similar for MTL, but now all we are doing is tying in time bounds. So now I can start saying things like between time t1 and t2, the proposition P should be true. And then the interesting thing happens when we combine these operators. For example, we can combine always and eventually to check that P should be true always, eventually, in some time interval. This is a liveliness condition. Or we can make correlations if P is always true in a time interval, then Q is always true in the time interval. To start off, I'll go into our multi-agent system model. We adopt a leader-follower-like model where we have a single leader agent. As you can see right here, we model single integrator dynamics, and for our target agents, we model them as these dynamics right here, where there's going to be some repulsive interaction between the leader based on the distance. And our goal is going to be to regulate these target agents to a desired goal location. And the challenges that we're going to see are that the target agents are non-cooperative, the agents are subject to dynamics that are nonlinear, and we have no direct control of the target agents. To design our control laws, we'll first define some tracking errors. Here you see E is a tracking error between the target agent and the goal location, and eta is a tracking error between a desired input that we have to design and the leader's position. And the important thing about eta is that we do not have direct control of the target agent, so we will use eta in our state feedback law to indirectly influence the target agent through the leader's position. And here on the right you see the control design for the virtual input and the control input of the leader. And to give you a better picture of what's happening is that here the target is in red and the leader is in blue, and what's going to happen is that the target will try to run away from the leader, but what our control design does is it will maneuver the leader agent in such a way that it'll regulate the target towards the goal location. But we have to note that this is given that we must tell the controller which agent to track, but we still have to design a signal that indicates what agent to chase. As I just stated in the previous slide, our strategy is to control the leader agent in such a way that it chases down the target agent to a desired goal location. However, due to limited capabilities of the leader agent, being only able to chase one target agent at a time, when a target is being chased, the remaining targets are being unchased, meaning that although one target may be getting regulated to the location, the others may be actually diverging from the goal location. So to analyze our system, what we do is we model this as a switch system model, and we will analyze the state trajectories of each agent while in each operating mode. And then what ends up happening is that from this model, we're able to extract some sort of knowledge on how our Lyapunov function evolves over time. So then we see that when it's in the unchased mode, we're able to develop a bound on how the Lyapunov function will grow. And when it is in the chase mode, we're able to develop a bound on how it converges. And with this model, then the next question is, how long should each agent remain in each mode in order to ensure that our control objective is achieved? Now from our switch systems model, we are able to extract dwell time conditions on our switching signal, and if we're able to satisfy those conditions, we'll ensure stability of our switch system. So this first condition here is the maximum dwell time, and what that gives us is the maximum amount of time that the agent can remain in the unchased mode. And the second condition here is the minimum dwell time, which gives us a minimum bound on the amount of time the agent must be chased. So the problem now is that we still don't have our switch signal. As I said, the dwell times are only a constraint on the switch signal, but don't give us a switching signal. That is, we still have to decide a rule to tell the controller which agent to chase. So our goal is going to be design a switching signal that satisfies the dwell times. Now, using metric temporal logic that was introduced earlier, we can start writing down these dwell time conditions as high-level specifications in MTL. And for encoding the maximum dwell time, we want to prescribe the behavior. The leader agent should chase each target agent for a specified amount of time. And using MTL, we can encode this specification in phi1 right here. And notice that this is where we're able to embed the switching signal. And now for encoding the minimum dwell time, we want to prescribe the behavior. Once the target agent enters the chase mode, the leader agent should chase the target for a specified amount of time. And this specification is encoded in phi2. And the main takeaway from this slide is using temporal logic, we can start characterizing high-level specifications into formulas. And if I satisfy these formulas, I will be able to ensure my system is stable. And then the use of these formulas will become apparent in the next slides. So far in the switch system analysis, we've developed dual-time conditions at low-level controller to ensure stability. Specifically, we develop a control law for the leader that regulates the target to a desired goal location. And as a result, we are left with the design degree of freedom to design a switching signal for the leader. That is, we still must tell the leader which agent to go to. And to synthesize the switching signal, we formulate a constrained optimization problem, as you see right here. And in this formulation, we solve for a switching input that minimizes a specified cost function that is subject to some constraints. And specifically, this constraint here is a dynamic constraint. And what this is saying is, based on how I know the agents will move, the leader will pick a control input that minimizes the cost. And this constraint is a constraint on our switching signal that says at any given time, only one follower should be chased. And this is a problem-specific constraint. And this constraint here is where the MTL formulas come into play. This constraint says the input I generate must satisfy my MTL formulas, which I've encoded my dwell times in. And again, solving this optimization problem gives me a switching signal. And previously, I designed a low-level controller to regulate an arbitrary target. So now I can apply the generated switching signal to the low-level controller. And what this does is it gives the low-level controller a sequence of actions that essentially says, chase this target during this time interval. And that wraps up my presentation for today. Thank you for tuning in, and listed below is my contact information. Please feel free to reach out to me for any further questions, and also listed below are links to the Nonlinear Control and Robotics Lab's websites, where you can find more information on similar areas of research that my group does, and links to our social media. Check those out and connect with us. Thank you, and enjoy the rest of the CDC conference.